So now we want to see what effect our symmetrization and or the anti-symmetrization of the wave function has on the canonical n-particle canonical partition function dvn. So we want to reconsider our ideal gas again, but now we take a definite symmetry of the wave function, so that I have k1, k2, kn. Antisymmetric, symmetric is given by, so we'll write them as n plus minus sum over eta p, k1, kp1, kp2, kpn, and the sum is over all possible permutations. Eta is plus minus 1, plus 1 for bosons and minus 1 for fermions. The canonical density matrix in the coordinate representation is then R1 prime, R2 prime, Rn prime, rho hat, R1, R2, Rn, antisymmetric, antisymmetric, symmetric, which is going to be 1 over Zn, the n-particle partition function, unrestricted. So this is a prime, we will come back to this, and then I have n plus minus whole square sum over p prime, eta p prime, R1 prime, Rn prime, kp1, kp2, kpn, and then I have kp1, kp2, kpn, e to the power minus beta h hat, kp1 prime, kp2 prime, sorry, kpn prime, and then I have kp1 prime, kp2 prime, kpn prime, I have R1, R2, Rn, right? Now this is a very complicated expression, but we can simplify this further. So I have z of n. This is this sigma prime is a restricted sum over k such that single particle states appear only once. But we can convert it into an unrestricted sum. And the way to do that is to realize that the total number of permutations possible is n factorial, but I also have the occupation number nk in the kth level, right? n1 particles in energy level 1, n2 particles in 2, so on and so forth, and the overcounting that I'm doing is product over k nk factorial. So if I now convert this restricted sum over k to an unrestricted sum over k, I am just overcounting this many number of states. So therefore I will divide by this which makes it product over k in k factorial divided by n factorial, and then the normalization is given by 1 over n factorial product over k in k factorial. I have a sum over p, which again I can take, which I can essentially manipulate, getting rid of one sum over p and bringing in a factor of n factorial and replacing this by the original unpermutated set. So I have, first I have eta of p r I prime ki. This is e to the power minus beta sum over alpha h square k alpha square over twice m, and then I have the permutated set of the k vectors kp prime I and ri. Good. A lot of things cancel out over here. This and this cancel out. After the cancellations, you see that this becomes 1 by Zn. The n factorial survives. I have a sum over k, I have a sum over p, eta of p, ri prime, ki, e to the power minus beta, sum over alpha, h bar square, k alpha square over twice m, and then I have the permutated set of the k vectors, ri. So this I realize is the coordinate representation of the wave function, and I can write down this as phi k of r as 1 by square root of v e to the power I k dot r, the single particle states. Let's just see whether we have everything that we have from the equation on top. I hope so. So then it is 1 by n factorial sum over p, we will interchange this, eta p, and then sum over k, and note that this particular sum, that is argument of the exponential, breaks into products. So I'm going to have a product over alpha equal to 1 to n. This is the complex conjugate of this wave function, so that, this is the wave function, so that this is going to be beta. So first let's write down k alpha square, this term, and then this is going to be, you're going to have 1 by v from these two, and then you're going to have I k alpha dot r prime alpha minus kp alpha dotted with r alpha. So 1 over Zn, 1 over n factorial, sum over p, eta p, product over alpha equal to 1 to n, sum over alpha 1 by v, sum over k, e to the power minus beta h bar square k square, k alpha square over twice m, e to the power I k alpha dotted with r prime alpha minus kp alpha dotted with r alpha. This sum over k, now I can convert it into an integral just as we did for a single particle case, and we are going to come up with eta p product over alpha equal to 1 to n, 1 by v integral v over 2 pi whole cube dk alpha minus beta h square k alpha square twice m e to the power I k alpha dot r prime alpha minus kp alpha dotted with r alpha. This integral is standard. We have done it also when we did the coordinate representation for a single particle, and this is going to give me 1 over Zn, 1 over n factorial, 1 over lambda t to the power n, sum over p, eta p, product over alpha, f of r prime alpha minus r of p alpha. Once you do the integral over k, this index gets transferred to this alpha, where f of r1 minus r2 is e to the power minus pi r1 minus r2 whole square over lambda t square. Now this is your r prime I rho hat ri, the coordinate representation of your density matrix. The partition function follows from the fact that the trace of this quantity is trace of the density matrix is going to be 1, and therefore z of n is going to be 1 over n factorial 1 over lambda t raised to the power n sum over p eta p integral dr1 dr2 all the way up to r to rn. I have a product over alpha f of r alpha minus r p alpha, which if you write down explicitly is going to be lambda t raised to the power n sum over p eta raised to the power p integral dr1 dr2 drn f of r1 minus rp1 f of r2 minus rp2 so on and so forth, and you have rn minus rpn. The quantum canonical partition function z of n essentially involves an sum over these n factorial possible permutations. So the idea is to consider first what this gives you. F of r1 minus rp1, f of r2 minus rp2, so on and so forth, all the way up to f of rn minus rpn. Right? Now, what is the lowest order of permutation? The lowest order of permutation is where p ri gives you ri. So there is no exchange. If there is no exchange, then you see the form of this is going to give you 1. If r1 and r2, which means r alpha, the set p alpha is identical to alpha, that means this function is 1, and therefore this sum f of r1 minus rp1, f of r2 minus rp2, so on, f of rn minus rpn is going to be 1 plus the second permutation is when I goes to j, that is going to be, and j, right, I less than j eta p is 1 is going to be fij fji. You have a pairwise. The third becomes I less than j less than k. You have fij fjk and k goes to I, and so on and so forth, higher orders. Now keeping up to the lowest order, I have z of n tvn is going to be 1 over n factorial 1 over lambda t raised to the power n, and then we explicitly write down this sum as first dr1 dr2 drn, and let's put the bracket 1 plus eta. So here in this particular term I have eta square, which is going to be 1 irrespective of whether it's a fermionic or a bosonic system. Sum over I less than j fij fji plus higher order terms. We'll ignore all other higher order terms. The first term is very easy to see. This integral is going to be v to the power n over lambda t to the power n. So let's keep it within the bracket so that it is easier. V to the power n plus eta times integral dr1 drn fij fji, right, with a sum over I less than j. Now how many possible pairs can you get? You can get n into n minus 1 by 2. If that is the case, then I have n factorial 1 over lambda t. I'm sorry, I missed out the n factor here. This is going to be v to the power n plus eta n into n minus 1 by 2. Now if I am choosing, let's say, R1 and R2, since there are n into n minus 1 pairs you can form by 2 number of pairs you can form, and if you choose any two pairs, all the pairs are identical, therefore you can just easily choose R1 and R2 and simply multiply this factor n into n minus 1 by 2, and then you see you are going to have dr1 and dr2. The rest of the integral over the coordinates is going to give you v to the power n minus 1. So we will rewrite this as v to the power n minus 1 integral dr1, sorry, n minus 2. There are two particles which have chosen R1 and R2. I am left out with n minus 2 of them. So v to the power n minus 2, I have dr1 dr2 f of r12 r21, and then I have higher order terms. This I can simplify further, and I can easily write this as 2 pi r1 minus r2 whole square divided by lambda t square plus higher order terms. Now to evaluate this integral, I can go to the center of mass frame, which means I choose R, because this is a function of R1 minus R2, so I go to the center of mass frame, which is R, and R12, which is the separation internal coordinates, which is R1 minus R2 by 2. And then essentially you will have 1 over n factorial 1 over lambda t raised to the power n v to the power n plus eta n into n minus 1 by 2 v to the power n minus 2 integral over dr12 e to the power minus twice by r1 minus r2 whole square over lambda square plus higher order terms, so that I have 1 over n factorial 1 over lambda t raised to the power n v to the power n eta n into n minus 1 by 2. Now the integrand over here, this part is the interesting part, because the argument of the exponential depends on r1 minus r2, but this term, the center of mass, is allowed to have the whole volume if you integrate over that. So this gives you v to the power n minus 1, and you are left out with d of r12 e to the power minus 2 pi r1 minus r2 whole square over lambda square plus this. A little more simplification follows, and we write them as v2 over lambda t raised to the power n, and I have 1 plus eta n into n minus 1 by twice v and I have dr e to the power minus twice by r square over lambda square. So this again is a Gaussian integral, and once you evaluate the Gaussian integral, you have v over lambda t raised to the power n 1 plus eta n into n minus 1 divided by twice v square root of 2 pi lambda square divided by 4 pi raised to the power whole cube plus higher order terms, so that I have 1 over n factorial v over lambda t raised to the power n 1 plus eta n into n minus 1 divided by 2v. The pi cancels out, this big gives you 2. So I have lambda cube divided by 2 to the power 3 by 2 plus higher order terms, which is going to be 1 over n factorial v over lambda t raised to the power n 1 plus eta n into n minus 1 times lambda t, the thermal de Broglie volume, 2 to the power 5 by 2 v plus higher order terms. The n particle canonical partition function now take this form. What is interesting is that now you see this 1 by n factorial has appeared very naturally within the theory. So when we started off with the naive assumption or naive construction of the wave function from the single particle states, we did not get this. But now we get this once we attach a definite symmetry to the wave function. The free energy F is minus kBt ln of Zn, which is minus kBt. I will have n ln v over lambda t plus ln of 1 plus eta n into n minus 1 over v lambda t 2 to the power 5 by 2 higher order terms minus ln of n factorial. So this is going to be minus kBt n ln v over lambda t and I can expand this log to write down this as eta n square over 2 to the power 5 by 2 v, where I have approximated for large enough n minus 1 is approximately n square minus n ln n plus n minus n kBt ln v over lambda t plus rho eta, sorry, there is a lambda t that is missing over here, rho eta lambda t over 2 to the power 5 by 2 minus ln n plus 1. The thermodynamic pressure P is minus del F del V T constant, and when T is constant, lambda T is also constant, capital lambda T is also constant, and therefore you have del F del V T constant is minus n kBt. The first term, the derivative of the first term gives you 1 by V plus eta lambda T over 2 to the power 5 by 2 times del rho del V, temperature constant, right? So there is going to be higher order terms which we have ignored when we expanded the log. Minus n kBt 1 over V plus eta lambda T raised to the power 2 to the power 5 by 2. Rho is n by V, and therefore del rho del V is minus n over V square. So I will have n over V square plus higher order terms. So that the pressure, which is minus of del V del F del V at temperature constant becomes N kBT 1 by V. If I take 1 by V outside, then you see I have the form which is N by V 1 plus eta lambda T over 2 to the power 5 by 2. Sorry, there is a minus sign that comes from this. Therefore, this is going to be a minus over here, minus times rho plus higher order terms. Now what you see over here, if I recast this as rho kVt 1 minus eta lambda t over 2 to the power 5 by 2 rho plus higher order terms. This is an equation of state, and the first term, this corresponds to an ideal gas result that we also have seen in classical statistical mechanics, but interestingly it has corrections over this. This is what is called a Vdl expansion, and it appears that even though we have started off with an ideal gas, the moment we give a symmetry to the wave function, the moment we say that the system is made up of indistinguishable particles, then we see that the equation of state tells us as if that the system is a interacting system, and this quantity is the second Vdl coefficient. That is the general expansion of the equation of state in terms of your density, right? So that you have B2 is equal to minus eta lambda T over 2 to the power 5 by 2. For a boson, eta is equal to plus 1, so that B2 is minus lambda T over 2 to the power 5 by 2. For a fermion, B2 is going to be minus plus lambda T over 2 to the power 5 by 2, where eta, since eta is going to be minus 1 for a fermion. So the resulting pressure correction is negative for a boson but is positive for a fermion. The second Vdl coefficient is actually obtained from the pair interaction, and for an interacting system, Fr is e to the power beta minus beta Vr minus 1, and for our case this quantity is e to the power minus 2 pi r square over lambda square. This part comes in if you look at this and this, so that e to the power minus beta of Vr is going to be 1 plus eta e to the power minus 2 pi r square over lambda square, and therefore the effective pair interaction between the particles is given by minus kBt ln of 1 plus eta e to the power minus 2 pi r square over lambda square. Now at very high temperatures, when lambda is large, and therefore I can approximate Vr as minus kBt eta e to the power minus 2 pi r square over lambda square. So this is the large temperature approximation of V of R. Now clearly you see that for a fermionic system, where eta is minus 1, this implies that the interaction is kBt e to the power minus 2 pi r square over lambda square. For a bosonic system, eta is equal to plus 1 and implies V of R is minus kBt e to the power minus 2 pi r square over lambda square. So the interaction is attractive for bosons but is repulsive for fermions. One can plot this also, and if you plot V of r, this is going to go like this way for a fermionic system, and it's going to go like this way for a bosonic system. So this is as a function of r.